We're continuing to look at rotational motion as opposed to translational motion, where an object is round and can rotate. Now, all of the rotation that we will discuss does not involve slipping. So the object is using completely the static coefficient of friction to roll. So as it rolls one revolution, the translation that it covers is 2 pi r, the circumference. So it doesn't slip forward and still spin the way many objects do. The SSAT in physics does not look at that case, the slipping case. Or as my Russian physics teacher put it, the sleeping case. When the object sleeps. Why would an object sleep? I don't know. So we're looking at angular momentum, which is the equivalent in the rolling world of linear momentum equals mv. So angular momentum is called L, and it is the rotational mass I. Remember, the moment of inertia is how the mass is distributed around the axis of rotation. So here is one possible axis of rotation. Here is another possible axis of rotation, and yet another possible axis of rotation. So depending upon the axis of rotation, we will have different values of the moment of inertia, and that is rotational mass, and omega is the rotational equivalent of v. And remember, if you're not slipping, linear guy equals rotational guy times the radius around which the object is rotating. So, and that is only true when the object is not sleeping. Oops, sorry. So, angular momentum, like linear momentum, is always conserved, will not change. Thus, your before angular momentum is equal to your after angular momentum. And if you think that both linear and angular momentum are being involved in the same problem, and they will be in just a second, you have to transform the linear momentum into angular. How do you do that? Well, the angular momentum is I omega, but remember I, for the case of, in this case I have a ball that and a rotation point P, so the ball is going to rotate around this point that's R away from where it is located. So it's mr squared, 1 mr squared, times omega, which is v over r. One of the r's cancels, and I get mrv, which is linear momentum times the radius. So the units are different for angular momentum and linear momentum, so they cannot both be conserved, nor can they be compared, because the units are different. It's like comparing time to velocity. They're different animals in the world of physics. So the units of angular momentum are kilogram meters squared per second, as opposed to the units are, why did I write the same units? Oh yeah, because MRV is kilograms meters squared per second, but for linear momentum, P, we have kilograms, which is mass, times velocity, which is meters per second. So there's an extra meters on top for angular momentum. This is one of those equations that you should memorize, although it really doesn't require memorization because you already know that P equals mv, and for every linear equation, there's an angular analog. So P equals mv, L in the rotation is rotational mass, moment of inertia, times rotational velocity, which is omega in radians per second. Here's an example. Cleverly marked example. That's how I know it's an example. So I have some kind of board or ruler of length L and mass M, and I have a ball which is sticky, so it's going to hit this hanging bar, and it's going to stick to it, and they're going to move together as one. They're going to rotate as one object around point P at the top. So I cannot talk about mv because that is linear momentum. I have to transform this into angular momentum, which is mlv. It is going to be mr squared, which is going to be I for the ball, times omega, which is v over r. One of the r's cancels, and I get mrv. In this case, I've called rl, the length of the board. It doesn't matter what we name things. It's the concept of the fact that the ball is moving at a distance away from the rotation point. So this is before, and this is after, when the ball sticks to the bar of length L, and it will rotate up at some omega, and it itself will have some velocity v, which is going to be equal to omega times L in this case. Point A, which is this point here at the bottom, is going to move with this velocity. So this is the angular momentum before the collision. And what is the moment of inertia of this item? It's the moment of inertia of the bar around the end, which is 1/3 ml squared. Remember, we found that by taking a 1/12 ml squared around this, and we used the parallel axis theorem, and we moved parallel to it a new axis of rotation, L over 2, and our new I is our old I plus m L over 2 squared. So the parallel axis theorem tells us that we have to now consider it to be 1/3. It's bigger because it's harder to rotate the object around this axis. Oops. Wonderful! As opposed to rotating around this axis, which is easier. So the moment of inertia of this object is the sum of the moment of inertia of the bar, 1/3 ml squared, plus the ball, ml squared. Little m, they're different masses. They don't have to be. And L is equal to I omega, so I take this I and I multiply by omega, which is V over L for the non-slipping case. And therefore, I set the before angular momentum, L before, equal to L after. And by equating them, I can solve for the only thing I don't know, which is the velocity of point A, V sub A. And so I cancel the L's out, and I divide by 1/3 capital M plus little m, the mass of the ball, the mass of the bar, and I get the velocity of point A is this ugly mess here. So notice that it is less than the original velocity because some of the energy of the ball has to go into rotating the bar, and so that means that velocity will be lost. Energy will be lost to sound as this hits, to deflection and bending of the bar. And heat as they hit. If you don't believe that friction causes heat, you can warm up a squash ball or a tennis ball by bouncing it into the ground and then hold it. You'll see that it's warmer after several bounces because the friction has been lost to heat. So that's an example of setting the angular momentum before equal to the angular momentum after to come up with the velocity of the combined object once the ball has attached itself to the bar. So there's an example of the use of the conservation of angular momentum.